Hi, everybody. My name is Figueroa, and I'm an associate professor of physics at Stony Brook University. And I also hold a joint appointment at Brookhaven and National Laboratory, where I'm currently the scientific leader of one of the largest quantum internet testbeds in the United States. As the United States is currently in a critical juncture when international competition in the quantum sector is rapidly expanding, it is necessary to have a critical discussion as to how the United States can remain as the leading element in this quantum technology race. To start our conversation, I would like to address the question, what is quantum technology useful for? What is its potential? In order to answer this question, as indicated by our previous speakers, we must look at the world in a fundamentally new way. In this quantum world, objects can be in different states at the same time, a concept very nicely described by Monica as quantum superposition. Much as Schrodinger's cat can be considered both dead and alive simultaneously, quantum particles can be placed in superpositions. And the most important thing is that these can then be used to hold and process larger amounts of information. Along these lines, and in analogy to what people say a mother feels the pain of her children from long distances due to their bond that they share at birth, quantum particles can be engineered to feel each other, although they are a universe apart. This interaction that Einstein called spooky interaction at a distance is the concept of quantum entanglement, and it can be theoretically used to move large amounts of information, thus realizing Star Trek style quantum teleportation. As mentioned by our previous speakers, technologies based upon these quantum principles will lead to a wave of new systems that will help solve many of today's global challenges. In each of these applications, quantum technologies could result in revolutionary improvements in terms of information capacity, processing speed, and sensing accuracy. Indeed, some of these technologies could be the decisive factor for further success in many industries and markets. Next slide, please. Echoing what was said already by our distinguished speakers, I will now list instances of these groundbreaking technologies that are currently under development and that have achieved a large degree of maturity. For example, quantum computers are expected to be able to solve in a few minutes problems that are unsolvable by the supercomputers of today and maybe tomorrow. This, in turn, will seed new paradigms in machine learning and artificial intelligence, just as described in our previous talk. Additionally, quantum simulators in which controllable quantum processes can be engineered on demand will give rise to new simulation techniques well beyond current capabilities, allowing the design of new materials and chemical processes. Additionally, arrays of quantum sensitive devices will give rise to new clocks and sensors with unprecedented sensitivity and accuracy, with potential impact in navigation, online medical diagnostic, and the synchronization of future smart networks. Lastly, and very importantly, an internet of interconnected quantum devices communicating via entanglement, the so-called quantum Internet of Things, will open new possibilities to transfer large amounts of data in an unconditionally secure way, making eavesdropping impossible. These transformative applications vary in their technical maturity, with some being close to commercial products within a relatively short time, while others might require more than a decade of research and development before being ready for commercial application. Further developments in these leading areas of quantum technology can be expected to produce transformative applications with important economic impact on the United States market, and also very importantly, real impact on ordinary people, just as the internet did 2 decades ago. Next slide, please. Nowadays, the effort of the quantum community has shifted towards designing and implementing first instances of large engineering quantum systems using many particles, quantum superposition, and entanglement. This is what we call these days quantum 2.0 systems. And we are really targeting that this system will push the frontiers of science and information technology. Examples of such large quantum systems are networks of quantum computers and simulators, quantum communication networks that use entanglement, and network arrays of quantum sensors. These large engineered quantum systems are primed to show first demonstrations of quantum advantage and should be the basis for new unforeseen key applications. As history has shown, for example, with the development of the laser and its large number of applications, including today's internet, disruptive technologies invariably create their own future applications. This undoubtedly will be the case with quantum technologies. Lastly, I would like to stress the need for a nationwide effort to address the challenges of realizing these large quantum 2.0 engineered systems. The American Quantum Initiative Act has been an extraordinary effort to form large interdisciplinary teams, including national laboratories from the Department of Energy and a plethora of academic institutions, in order to solve these aforementioned quantum 2.0 big challenges. However, a decades-long sustained effort, I think, is still required to unlock the full potential of all these quantum technologies and to accelerate their development to bring commercial products to public and the private market. This nationwide sustained quantum program, a reinvigorated national quantum initiative that perhaps is only comparable to the effort that many decades ago was required to get a man in the moon, should include efforts in many different directions, including the discovering and implementation of killer applications that can be realized only using these quantum 2.0 solutions, realizing new applications of quantum information science in broader areas of science, and discussing some of the previous videos, to form a scientific and industrial economic ecosystem that will enable the eventual commercial success of quantum 2.0 technologies, and, as mentioned before, to grow a new quantum smart workforce, including a young and diverse set of members suited to bringing quantum technologies into practice. As you can see, the quantum future of the nation looks very bright. I think that with additional resources, we foresee decades of new quantum-assisted scientific discovery and the formation of a quantum economic development ecosystem that will realize the promises of these fascinating new technologies. Thank you very kindly for your attention.